please. Ooh, been a long week. Welcome, everybody. You see mostly familiar faces here. For those joining us on the recording later, or who haven't joined us, been here before, this is Tucson Amateur Astronomy's Fundamentals Group. We meet once a month on the second Thursday, where we go have presentations and talk discussion on two topics in astronomy. One is bouncing back and forth between a constellation and an astronomer for a point of interest of the month, and then a second larger main topic, which can cover generally anything in astronomy that whether it's active research areas that might be of interest, or in helping us learn more about things to go look at in the night sky. So tonight, I will be leading off with our astronomer of the month, Johannes Hevelius, and we will follow it up with Pete Hermes, who will be talking about gravitational waves and multi-messenger astronomy. If you do have questions, I do have the chat visible, but you're also free to interrupt me at any time. Take a lot of questions of that. So jumping right into it with Johann's early life. He was born in the 1600s to two Polish parents in the city of Danzig, which is in modern day Poland, near the city of modern day Gdansk. Danzig was eventually renamed after World War II and the Germans and the split between the Germans and the Soviets. He and his family were Lutheran Christians, and they were pretty wealthy merchants within the city, and they ran a very profitable brewery, which you'll see with a lot of later things where this is where a lot of what funded a lot of Johann's abilities to engage in his astronomy hobby. For those who are beer aficionados, they brewed a variety of beer known as Yappen beer. I hope I'm using that correct J right. I'm not sure if that's a soft J or a hard J. He had three brothers and six sisters, but all of his brothers died in early childhood, and I could not find any more information about his sisters. Uh, but today, elements of his family still live in the city of Gdansk, excuse me, and they are actually patrons to local astronomer groups and will and support outreach activities within the city amongst some of them, which I thought was a very interesting thing to see. Modern continuation of historical astronomers, which we hadn't actually seen before when bringing up these people. He went through some being from a modestly wealthy family. He was able to actually go through some element of school during his childhood, attending 6 years of basic education at the gymnasium in Danzig, where he would then go on to study Polish in a city known as Gondelstex. I'm not going to get any of these names correctly, but oh well. Where while he was at this second school, is where he would eventually meet his first astronomy and mathematics teacher, Peter Kruger. Peter would elicit his help on various tasks and also teach Johann how to use a variety of the astronomical tools at his disposal. After graduating from this unnamed school in Gdansk, he would go on to do some traveling and would spend time learning jurisprudence at Leiden University in the Netherlands, and then spontaneously just randomly travel around Europe and England for some time before eventually returning back home in 1634. None of those things would come and matter in his life for a while, though. Upon returning home, within about a year, he married his first wife, Katrina Berbesks, who was one of his neighbors 2 doors down, and who was also from a fairly wealthy family of merchants. I did not find any record if the two had any children, but Katrina ultimately died in 1662, where Johannes would then go on to remarry a 16-year-old girl known as Elizabeth Koopman, and the two would go on to have 4 children, which is one of those like researching this, my modern day sensibility is just like, ugh. just from that age gap. But funnily enough, Elizabeth would actually become one of Johann's best assistants. And by some measures, and depending on which historian you want to believe on this, in terms of like interpretation, she was arguably one of the first modern female astronomers, preceding Carolyn Herschel by which I think is one of the more prominent ones that we've discussed by some time. So after returning home and marrying down and setting on, Johann did what a lot of us wish we could do, but they had a lot of money at their disposal. And he built an observatory in his house, specifically three of his houses, because he owned three houses and they were all interconnected to each other. And so he built his observatory on top of them. And this included, and there's pictures of this in some upcoming slides because I just found it hilarious at how big this thing is, a 46-meter focal length refractor with an 8-inch aperture. This thing is 46 meters long and it just hangs and it's ridiculous. And was using his own funds, was able to also furnish a lot of other tools. Well, one of them is on a picture on the right here, which depicts Johannes and Elizabeth using a sextant in his observatory to take measurements. And the observatory would eventually come to be known both by, I'm not sure if this was given a name given by the locals or by some other visitors, would come to be known as the Star Castle. His observatory earned him the patronage of 4 different kings of Poland, and would also be a measure in which earned him a ratified title of nobility within the Polish aristocracy. Excuse me, couldn't think of that word for a second. The observatory itself would see repeated visits by numerous elements of the Polish royalty and some elements of the French royalty, where the French monarchy also commissioned some work from Johann's, which was then exclusive to the French government for some other things. But beneficially enough to him is this fame, having your name known amongst royalty gave him a tax break, and he didn't have to pay taxes on either liquor he sold within the city. He could actually export it, so it was a big deal. So it made him a lot more money from this to help keep funding his astronomy work. Key to his overall success, outside of him just being very wealthy as a merchant, was that he was also very gifted as an artist, which was not technically very common amongst some of the early astronomers. I mean, they could draw to a certain extent, but they typically had other artisans help them when making their certain elements for publishing, particularly the copper plates, which were used to transfer their drawings or sketches into books for publishing. But Johannes was able to do all this himself, which gave his drawings much greater accuracy than the transpose process of describing to an artist or helping an artist recreate the observations. With all of this work in 1664, he was then inducted into the English Royal Society, or that should be British Royal Society, or same thing, as one of the first international members and first non-British members. Well, that same thing, but you get the point. Unfortunately for Johannes, his observatory and most of his research and notes was destroyed in a fire in 1679. And although he would go on to rebuild it and his 46-meter refractor and his wife, it is ultimately he did die about 8 years after this fire from old age, but also by some measures he was, quote, distraught from the loss of his observatory and most of his life's work. So this is the first of 2 pictures depicting Johann's 46-meter refractor. As you can see, this is very ridiculous, and he had it on top of his house, as can be seen here. He just mounted this thing on top of 3 houses and just drew a giant patio for it and just brought people up to go look through it. It is one of those things where you just feel like this is that one guy who has all the neighbors around it goes like, oh, that guy. The guy who makes all that racket on our roofs.
Hey, Connor.
Am I breaking up?
No, I just have a question. I'm sorry.
Mm-hmm.
Okay, this is right around the 1630s.
Yeah.
Okay, and I mean that physically, that thing is 46 meters long.
And the focal length is 46 meters. I'm not sure if that's the actual thing, but given refractors are usually a 1-to-1 on that, it would be a safe assumption to say.
or at
It's like
most
100,
1 to 1.5, maybe.
probably.
Yeah, because I was just sort of curious because when you first mentioned that, and I went back and looked real quick. I mean, the first telescopes weren't developed till very early in that century, and here it is, roughly 26 years later, and you've got this monstrosity, which is kind of remarkable. I think given
Yeah.
when telescopes were first used. So
But
okay,
going back to this previous picture, as you can see, this is not an enclosed system that he
right.
builds. It's basically a very massive series of glass held between rings, and this thing was very susceptible to wind, and somehow it was still viable. I look at this and I just go, how does this even work? But I mean, also considering that light pollution wasn't really much of a thing back in those days, it really didn't need a lot of the things that we would need, like,
Okay.
an enclosed tube or things like, even though they would ultimately help it, but you'd have weight constraints to deal with.
Very good. Thanks.
Oh, also because it was hidden by those slides, this thing had an f225 focal ratio. This was not the fastest of telescopes at all. Still really big and one of those bragging rights.
But think about the magnification you would get, though.
Well, I mean, the glass itself probably wasn't all that great when you have all those multiple lenses going through it. So it's arguable how effective it actually was by, even by, a pair of binoculars by today's standards. Um, so over the course of his very long career in astronomy, he had a very interesting dispute with British astronomer Robert Hooke on what was the most accurate and effective way to take measurements. Hooke himself was like, you should use a telescope. It's all better. We can do more things with this. We could be more accurate. And Johann was like, no, very politely, though, to Robert Hooke, although Hooke, uh, by many accounts, was not exactly the easiest person to talk to or agree with in any way. He was very much not well liked amongst the professional astronomy community of his era. But as he was on this debate in 1679, shortly before the fire that would destroy his observatory, uh, Johannes was visited by Edmund Halley for a number of things, but the main thing was he was conned into visiting by his then to go and try to be another thorn in Johann's side to convince him to use a telescope to make his measurements. And Edmund Halley, being the slightly more educated British person that he was, went over to this Polish man's house. Wasn't really quite expecting knowing what to expect, but what also had low expectations on just how good his measurements were. Was like, I'm going to pick apart this guy's measurements, make his throw off, discredit all of his work, only to find out that Johann's measurements made purely with the sextant quadrant and a couple of other basic intervals out, even using a telescope, were better than Halley. So, uh, which very much interesting. And so, despite even with this, despite Haley's additional prodding, Johann was still affirmed, no, I'm not going to use a telescope to make my measurements for any of this. I can do much fine with the quadrant and Adelaide, which was a type of variation of like a quadrant and a sextant, which we haven't really seen before, and I don't have a picture of. Because of this, he is what some of the sources I was reading say one of the last astronomers to not use a telescope for the measurements in any of his major works. All of his works were done using, uh, excuse me, using other instruments.
Connor,
Yes.
can you slow down just a little bit? When you're talking real fast, you break up and it's that
I'm
sounds like
sorry.
that.
This is my head. I have three different headsets and they all have various issues with them. So, where did I leave off? Where would I start cutting out at? Like,
No, no, I mean you're okay right now.
but when I was speaking here, what do I need to go over again? Was my question.
No, you don't need to go over anything
Okay.
again. Just be aware that's happening.
I am familiar with it. Just it's hard to catch it because you can't hear it on my end. So just let me know if it happens again. There's not much I can do to fix it, unfortunately. Even talking slower won't help. So of the major works that Johann was well known for was being one of the producing an extremely then what was then an extremely accurate map of the moon. Galileo himself would also make map, and several other astronomers before him. But at this period, this Johannes was one of the most detailed and complete of the time, although complete here with an asterisk. And he would spend over 4 years assembling this map using his 46-meter refractor. It's kind of a distinction here between using this to make measurements and observations. So here he's observing and drawing what he's doing rather than taking angular measurements, which is what the argument that Edmund and Hooke and Halley were trying to persuade Johannes to do. In producing this map, he also discovered the libration, which is the natural wobble that the moon produces as it orbits the Earth, which allows us to see more than 50% of the moon throughout this cycle. And on the right is a depiction of what a standard libration looks like as the moon orbits the Earth. And you can notice that there's a very significant wobble of the moon, which is one of those things that's probably an astronomical league challenge to go and observe, Doug.
Yes, it is.
Oh, it's in there. Hey, Connor, another question. In fact, looking at the simulation, it's kind of neat. And Doug, maybe you can chime in or anybody else that's aware, but it certainly looks like the latitudinal libration is significantly greater than longitudinal. Yes, or is that an illusion?
Uh,
Especially when I look at that north end, it certainly looks like it varies a lot more than the limbs on the east or west sides.
That it
I,
might be slightly exaggerated because of, at least from an observer's perspective on the ground, because of the moon's own orbit. You won't probably, there's probably some fuzz here, I would have to say.
I couldn't tell you
Okay.
what's going on. I understand what you're saying and I see it, but I'm not sure I know the reason.
Okay. Or if in fact it is true. I mean, I can go in and take a look at it because the atlases provide that information, and you can see the variation as you go through a cycle. And I guess it's just a matter of looking at the two values to see if there is, point in fact, a greater amount on that north-south side as opposed to east-west limbs. Okay, thank you.
So this is a copy and reproduction of Johann's map that he made and eventually published, just showing the two overlaid spheres to show how much the full body of the moon and where you can see it at different points in its libration cycle. So going off of this, yes, the north-south tilt would definitely be significantly more than the east-west tilt, which you were referring to, Pete. So being a map maker, he also liked to name a whole bunch of things. And although many of the names that he established for lunar features are no longer in use, some of them still are. The only one I was able to find definitively without spending hours through random reference books was a feature known as Mont Alps, or the Alp mounts, named after the Alps in Europe. And although not necessarily named by himself, eventually there is a crater that currently bears his name on the moon in his honor. Unfortunately, the copper engraving of his original map has since been lost. There's one telling that saying that somebody decided to melt it down and turn it into a teapot.
Oh.
So this was not apparently destroyed in the fire that took his observatory down, but there are the published copies that survive of his map, not just the original engraving that was used to produce those copies was destroyed. And his work on producing this map is what has resulted in him getting the title of the founder of lunar topography. He's also credited in many of his observations of creating or defining, 10 constellations, which was until modern standardization by the IAU in the early 20th century, was every astronomer's favorite pastime to go and make their own constellations, publish them in the Star Atlas, and hope they stick. 7 of those constellations that Hevelius Johannes named are actually still in use today. They are Canis Venatici, Lacerta, Leo Minor, Lynx, Scutum, Sextans, and Vulpecula. 3 constellations that are no longer in use, and I do have star charts of 2 of them to show you where they were, are Cerberus, Mons Menaelis, and Triangulum Minus. Oh, big words. Cerberus was absorbed into the constellation Hercules. Menaelis was just south of Arcturus and is now entirely within the bounds of the modern constellation Pleiades. And Triangulum Minus was just turned in Triangulum. So this is just showing Triangulum Minus and Triangulum Majus, not major or minor, interestingly enough here, which are roughly in the same position today as just Triangulum itself. So that was why it was just turned into 1 constellation instead of 2 for simplicity. And Cerberus itself is kind of hanging off. So this is the constellation Hercules, and he just named this area where that Hercules had in his outstretched hand of like Cerberus, although these to me look like the heads of a Hydra because of their serpentine form in this drawing. And then I do not have one for the Menaelis constellation. Wrapping this up here, his other significant achievements, some of which we've talked about before, is he was the original discoverer that Mira was of the star Mira, and the fact that Mira is a variable star. He is credited with discovering 4 comets, although I could not find the names for any of them, which suggests to me that they are either long period comets that were coming through or were disintegrated or destroyed by the sun, so that they stop being comets. He was also a significant observer of sunspots, and over the course of his life, he produced a catalog of 1,500 stars with a variety of very precise measurements. But this was not published during his lifetime, and it was actually one of the several articles that was published by his wife Elizabeth upon his death. And it is from one of these latter documents is where we just learned about the constellations that he himself described. Questions or comments?
Bravo, Connor. Thank you.
And I need to make Pete co-host so he can actually share for his stuff. And I'm gonna.
I can give a little insight on that large refractor. In the early days, they didn't know how to grind the glass very accurately to make like an F10 refractor has a lot of curvature to the lens, and you had to have, like today, you have 2 pieces of glass with a different index of refraction to actually make it work. But you could also, it's essentially a magnifying glass, a single piece of glass for the lens, and its ground, the 2 surfaces are almost parallel. There isn't a lot of curvature to it, so that's why it has such an extreme focal length. But it works in the sense that you can look at things and get a magnified image.
Thanks, Doug, for the insight. Pete, since there doesn't seem to be any questions or comments, unless I just not.
Well, I thought it was a great presentation, Connor.
I was actually kind of surprised on some of the things with him. I wasn't necessarily expecting going into this being a moon presentation, given Artemis 2, which was very much not an intended thing on my part. That was one of those happy accidents of like, hey, so it was very much not me trying to ride the Artemis 2 frenzy right now. Although they do have some cool pictures of Artemis 2 coming out from NASA. Anyway, as I mentioned, we're on to Pete and his discussion on multi-messenger astronomy. Take it, Pete.
Thank you. Yes, good evening. Yes, it is on multi-messenger astronomy, not just gravity wave astronomy, although that is a part of that. And I certainly thank you for your attention here. Just to give you an idea, one of the things we're going to talk about, we're certainly going to talk about what we refer to as regular optical or visual astronomy, because that is part of this whole large set. But some of the newer conventions, some of the newer developments over the past 3, 4, and 5 decades have dealt with a lot of these events or objects that especially emit higher energies, and it's across the spectrum, across all these different avenues, and we'll get into that a little bit. But this, opening picture here just tries to capture some of that. Now, capture all of it, but we'll continue on. Let's see if I can get my. There we go. Okay, so anyhow, multi-messenger astronomy, coordinated observation and interpretation, multiple signals, electromagnetic radiation, which includes, infrared, visible, X-ray, and of course, we're more familiar probably with the visible or optical types of astronomy, gravity waves, neutrinos, and cosmic rays. To date, there are a lot of observatories scattered all over the globe and in space, and we'll get into some of the reasons why it's necessary to have some of these telescopes, detectors put into space to improve their ability to capture information, to capture data. But this is one representation, especially showing some of these more high energy events. We talk about either a same event or object, and of course, an event can occur over a period of time, in a determined period of time. But as an example, here you have a supermassive black hole binaries at the core of a galaxy, and I'm just talking, hypothetically, it could be any galaxy, producing electromagnetic waves at radio to gamma ray wavelengths, detected by telescopes on Earth and in space, because we have, basically optical and visual astronomy going on both from the surface of the planet and in space, that can be studied through their effects in an array of radio pulsars. So, which are some fairly high energy events. This is just a simple table that shows some of these different types of events. You see the event along the left side: solar flare, supernova, neutron star merger, blazar, active galactic nucleus, and tidal disruption event. From the standpoint of sources, generally, solar flare is certainly something that would be within the limits of our solar system, or the heliosphere. And all these other events or objects are outside of that. And so that's one of the things that multi-messenger astronomy certainly captures. Certainly, it can capture a lot of events or objects inside our solar system, but it can also be more useful, more valuable in taking a look at or studying or gathering data information on events and objects outside of our heliosphere. And that's the case of just about every single one beyond the solar flare. What you can see, we talk about electromagnetic. Remember, that includes both visual and then those things, radio being the longer wavelength, over towards gamma ray, the shorter wavelength. That's all within the EM or electromagnetic spectrum. Cosmic rays, gravitational waves, neutrinos, and then an example of each one. This one is a solar flare. With respect to the solar flare, this is an estimate, likely one from 1942, thereby the nomenclature. I think it's just strictly a date. I think there was one more recently in 2003 that was probably subject to some more advanced studies with respect to multi-messenger astronomy. But certainly we would expect electromagnetic effects, cosmic ray effects on a solar flare. With respect to supernova, and you'll see some of this in a little bit more detail. I'm not going to get very technical with the presentation because, one, I don't fully understand it, and Doug, I will call on you if chime in at any point, especially when we start talking about the physics of some of these different types of detections that go on. But certainly supernova, there are electromagnetic effects. You can see them. It's predicted, of course, that they would emit gravitational waves. This hasn't been accomplished yet, but more than likely, this might provide a precursor to a supernova existing, or in the case of a neutrino detections. Neutrino detections are very difficult to make. But we would certainly imagine, with the example of a supernova from 1987, which is probably one of the most well-known first examples where we had the technological capability to observe this particular event over a period of time with a lot of different methods. Neutron star merger, with respect, yeah, there's going to be an EM indication, gravitational wave, most definitely. Neutrinos are predicted. We don't know that for a fact because it hasn't happened yet. Blazar is basically a pulsar that will have, as I understand it, some of these jets that emit from the top or bottom of the pulsar itself and put out an a large amount of energy. More than likely, we might be able to see them. Well, I shouldn't say we'd be able to see them. Be detected through electromagnetic radiation. Cosmic rays, maybe. We don't know for sure. Neutrinos, more than likely. And there is an event where this has supposedly occurred. The TX actually stands for Texas. There's a Texas catalog dealing with some of these blazar events or objects that have been observed. Active galactic nucleus, this is where you more than likely have the existence of a supermassive black hole at the center of a galaxy. In a lot of cases, a lot of the galaxies that we're able to see, both ground-based, more likely space-based astronomy, uh, there's not all galaxies will necessarily have an active nucleus, and we may or may not be able to see it, but in some cases, we'll use these methods to try to verify it. Like I say, cosmic rays, as far as detection, not yet. More likely, neutrinos. Messier 77 is probably one of the better examples for something like this. Then tidal disruption. This is a case, I actually have a little graphic over there, and it's pretty much basically a star that's pretty much destroyed if it gets too close to a black hole. More or less, most of its material will disappear over a period of time, and in all likelihood, any one of the methods could be used to detect it. More than likely, if we were able to see it or with EM, very possible neutrinos, and likely with cosmic rays or gravitational waves to verify it. So anyhow, these are some examples and some of the different methods when we talk about multi-messenger, being able to both observe an event and maybe validate it from different aspects, if you would, or different methodologies being employed based on for lack of a better term, the terms that are used are photonic emissions, which are going to be in the electromagnetic range. And then the non-photonic are going to be all the other ones, cosmic ray, gravitational waves, and neutrinos. So they're the non-photonics. Just a basic representation of the electromagnetic spectrum, basically dealing with radio waves, which are the longer wavelengths you can see on the left, moving to the gamma rays, which are much shorter wavelengths and higher frequency. You see examples going across, visual examples with respect to some of the outputs, the frequencies, and then in a lot of cases, most of this radiation, electromagnetic radiation, can be correlated to a temperature output of the various objects. Certainly, we take a look at something like our sun. We know that's around, I think it's about 5,000 Kelvin, if I remember correctly. And of course, a lot of that is going to be in the visible, but there are also portions that are not necessarily in the electromagnetic spectrum. They're going to be on the far outreaches. And we're going to discover that, there is a potential to detect and measure and take a look at the cosmic ray output from our sun, whether or not there's a flare or not. Okay, in dealing with electromagnetic radiation, here again, we go and take a look at those longer wavelengths. That's radio astronomy. It's been around for a long time. Typically, radio astronomy can involve a single, but more than likely, multiple antennas. It can be done during the day, which is kind of a nice thing about radio astronomy. You don't need the night skies. Low frequency limit around 15 megahertz, which is about 10 meters in wavelength. The ionosphere does affect, and certainly the atmosphere does affect radio waves, although we will discover, and you'll see another graphic where a lot of, most of radio astronomy can be done from the surface of the planet. However, in this case, putting a radio, an antenna at higher altitudes, elevations, or in remote areas is going to be preferred for other reasons. There are radio frequency limits. Remote locations are preferred. The graphic you see at the bottom of the graphics going across on the right. The Very Large Array in New Mexico is shown on the right, and then the Green Bank antenna out on the East Coast shown on the bottom right there. And then the bottom graphic is a shadow of the black hole at the center of M87. This was reported out, 2 or 3 years ago as the first imaging of a black hole. And a lot of that was accomplished with radio astronomy antennas scattered throughout the globe. I don't want to get into the physics of it, but radio astronomy and certainly other aspects of astronomy, even of the different types, will use a methodology called interferometry, where you can take a number of detectors, and you can do the same thing with visual scopes too. This works really good with radio telescopes, but actually have telescopes at different locations on the globe. And while they don't totally function as a sized antenna of the whole globe, they add significant capability and detection capability by using multiple antennas. Not only where you have the Very Large Array, where I think they're scattered across roughly, if I remember right, probably about, I think those are 2 mile. I'm going to guess they're about 2 mile spokes on each end. There's three of them, principally in the not the very highest elevations in New Mexico, but somewhat high plain area in central New Mexico. And I've flown over them a number of times and seen them released off to the side, not right over the top. But sometimes you'll see the antennas are spread out quite well, to the extended limits of the three spokes, and sometimes they're rolled back in. But nonetheless, that's something that can be accomplished with radio astronomy. It is subject to atmospheric effects, but probably the least affected of all the multiple types of detections. And of course, another infrared astronomy. This is something that typically is best performed from space. Of course, we know that one of the principal advantages gained with the James Webb, outside of being far enough from Earth, were the infrared cameras, two infrared cameras that were put on that particular telescope that provide some significantly greater capability with respect to imaging of objects and events, even to the point of going way outside of our galaxy even. But here again, the wavelength is roughly 0.75 to 300 micrometers. You can use mirrors, lenses, similar as those that are used in optical astronomy. Many of the wavelengths are absorbed by water, so thereby the reason of putting, the better infrared telescopes into outer space. But you'll see one example at the top there, and I don't know if you can make that out. That is Project Sophia, and I used to know I know for infrared is certainly in the title, but basically that's an antenna sticking out the port side of a 747 jumbo jet that was taken up to altitude, probably into the high 30,000s, and it was used to accomplish infrared astronomy. Here, the advantage gained was to get it high enough in the atmosphere where the effects of the atmosphere and the water vapor were minimized. They weren't removed, but they were minimized significantly. And until the development of infrared astronomy in space-based telescopes, that was about the best that could be expected at that point. Because, like I say, many of the wavelengths in infrared astronomy are absorbed by water, thereby the water vapor in our atmosphere. But infrared astronomy has been very beneficial, very useful on discovering star clusters, nebula, especially quasars, and extrasolar planets. And of course, we know that basically infrared astronomy is going to detect the heat energy coming off of a particular object, and just affords us a wider range to be able to look at, rather than just having to be satisfied with the visual wavelengths. Here's a representation of the various forms. If you go across, you can see, moving from radio astronomy on the right through microwave, infrared, X-ray, and gamma. And you can see that basically from the standpoint of ground-based telescopes, visual and radio are about it. Otherwise, just about everything either has to be at high altitude or space-based. Now, some of these high altitude, some of these methods have been employed, for instance, infrared astronomy and some of the other methods, and we'll talk about this. Sometimes high altitude balloons or sounding rockets were used, but these were for brief periods of time. The 747 doing infrared astronomy afforded a little bit more time, but of course, ideally is to have a fixed observatory on the ground or something up in orbit that will last for a period of time. And so there are a lot of things going on with respect to these various types of astronomy, but you get an idea. The red lines sort of show what can get through down to the ground. Otherwise, if it doesn't make it to the ground, it's pretty much, hampered by the atmosphere. Which isn't good, which is good in some respects, because certainly when it comes to gamma and X-rays, the surface of our planet is somewhat shielded by the atmosphere to some of these, not all, but most of this type of radiation, which is a good thing because gamma and X-rays aren't really good for biological entities such as ourselves. Okay, moving on further, electromagnetic radiation, visible light or optical astronomy, what we are used to mostly. That includes both space-based telescopes, large, and of course some of these observatories that we're seeing down in Chile, out in Hawaii, and scattered all over the planet are getting quite enormous. And of course, we have our own little 16-inch out at Timpa, which basically, sits in that same realm. Oldest and most participated in, of course, we're moving from wavelengths, 380 nanometers, which is the violet end, to the longer wavelength, 750 nanometers, which is the red. And of course, we're going to get ultraviolet to the left of that and infrared to the right of that, just outside of our visual limits. Light pollution and atmospheric effects are probably the greatest decrements to this type of astronomy. So certainly observatories being built at high altitudes on mountaintops works out good for ground-based. And of course, even better yet is to put something, to put an optical telescope out in space to remove all those effects completely. And certainly there are advantages, you were to have something, and this would apply to radio astronomy, if you were to have a radio telescope on the far side of the moon, or an optical observatory on the far side of the moon, as far as not having to rely on something space-based, that would be even better compared to the methods that we have available now. X-ray astronomy, specialized, but it has been around for a while. X-rays are largely absorbed by the atmosphere, thereby balloons, rockets, and now more likely space-based observatories, telescopes are used. And generally, X-ray astronomy works in the field of these emissions from extremely hot gases, million Kelvin to hundreds of million of Kelvin. So this is pretty significant, and generally it's going to be looking at rather large and distant objects. And you have a couple of examples, of I'm trying to remember, I can't remember if Chandra is still, I think it's still going as far as X-ray observations. And then, a particular star nebula in deep space being imaged using X-ray astronomy and not just relying simply on visible or optical astronomy. Gravitational waves. Okay, this gets into another area. A lot of this is based on, Einstein's theory of relativity, dealing with the curvature of space-time. Speed of light, these waves travel at the speed of light, and they're generally going to be associated with the motion of gravitating masses. When I talk about gravitating masses, really anything, for the most part, will send out gravitational waves. But the ones that are probably most detectable are going to be some of these more significant dramatic events that occur, such as neutron stars and black holes. But anyhow, the transport energy is a gravitational radiation. It's not something that can be explained with Newtonian physics. This is something that falls, completely under Einstein's theory of general relativity. Generally, the waves are not affected by any intervening matter. And like I said, some of the objects events that this particular type of astronomy is used to look at are binary systems of white dwarfs, neutron stars, and black holes, also supernova, and then going back and trying to study the Big Bang to some extent. There's actually a spectrum for this, and you can take a look and you can see some of the different events that are going on, and you get an idea. I'm just going to let you look at this for a while. This is, you have the wave period, you have the frequency, but it gives you a couple of examples of the different objects or events that gravitational astronomy, wave astronomy, can be used to look at. Quantum fluctuations in the early universe, going back to the Big Bang, supermassive black holes, compact binaries in our galaxy and beyond. Certainly, this is something that can be used particularly for events outside of our galaxy. And then you see some of the observatories are being used and some of the methods being employed. And then coming down here, this is probably one of the most well-known. These installations, I think, have been in existence for almost 2 decades now, but it's called LIGO, Laser Interferometer Gravitational Wave Observatory. And here again, this is, uses some of the principles of interferometry to take advantage of these distances. You have two observatories. One's up in the picture on the left, up in Hannaford, Washington, and the other one you see on the right there is a little bit closer in. Basically, they're set up the same, but this is in Louisiana. And so essentially what you have, you'll see, basically it has two arms when you look at the observatory itself, and those things go out about 4 kilometers. So 4 kilometers, oh God, what do we have? A little over 2 miles. They'll have the two arms going out. And these two objects are separated by approximately 1,100 kilometers. And so there that advantage is gained because what they're trying to measure is the difference in gravitational waves and basically a distance that amounts to a fraction of the width of a proton, okay? The principle is a little bit more complicated, but I've got a couple of simple models here that hopefully you'll understand. Basically, you see on the left picture, you see the two arms, one going up to the left and the arm going off to the left. And these are essentially the two arms you see here, where you have a test mass and you have basically lasers going out through these test masses and coming back to the center, okay? And you'll see where the beam splitter is. On the right, you're going to see a very simple diagram that shows what happens when a gravitational wave impacts these observatories. Up in one, up above in one is the steady state, nothing much going on. And down in 2 is when a gravitational wave is detected by it's going to be both of these observatories, but you can notice the waveform in the lower right there. You can see where it's split, as opposed to the one above it, where it heads into the purple circle. Can everyone see that pretty much? So here you have the steady state, and then you have where a gravitational wave has been detected. And essentially you have, a diagram of the physical portion of this. And so thereby the reason for these long legs of these observatories, trying to measure these, a very difficult, gravitational wave is a very difficult thing to detect. One of the things that these observatories had to deal with, and here again, remoteness is very much preferred, is that physically, seismically, and sonically, I think these observatories can be affected. So, for instance, a vehicle driving by one of the roads nearby, or a service vehicle, would be detected by the observatory. A phone ringing in one of the offices or one of the outer rooms of this observatory would affect the detectors. So it's something that has to be very controlled. Typically, what happens is, you can see when you look down at, the simple diagram I have here, try to explain it, showing the split wave down here in the lower right. Typically, what happens is with the gravitational wave detection, it can be put on a plot, and you can take a look at it, and you'll see that, if you take a look at the change in light flux of a star, whether especially if it's a variable or you're using that method to detect exoplanets. You can see the changes. And basically, this was what happens. You'll see something similar. And I wish I'd probably put one of these diagrams up. But there are various shapes of the forms that occur when a gravitational wave is detected. And sometimes, like I talked about a vehicle driving by the observatory, that has a very specific shape that over time has been noticed and cataloged. Similarly, a telephone ringing in an office building, that's another one that's happened enough where they've been able to catalog it. And so, the people that are using this form of astronomy have cataloged all these interferences so they can understand better when they obtain an actual gravitational wave. And typically, having two independent observatories in this case not only improves the interferometric capabilities, but also provides a method for validating a signal, because more than likely a gravitational wave is going to affect both observatories at the same time in the same manner. So that's one of the advantages of this. Here again, this, like I say, it's only been around for about 2 decades, but they've been online, and I'm going to guess right now, I'm only assuming that anywhere between maybe a dozen, possibly, I don't think 2 dozen detections have been made yet with respect to some of these events. Neutrino astronomy. This is something that's been around for about 3 decades, dealing with elementary particles interacting via the weak interaction and gravity. Okay, going back to some of the basic forces, we take a look at this. We have electromagnetic radiation, but dealing with some of the forces, the weak forces, strong forces, and or certainly gravity, and trying to take these various types of forces and being able to observe when they occur with a particular object or an event. And essentially, a neutrino just works in some of these other areas. A neutrino is neutrino is a particle. It's electrically neutral and extremely small rest mass, to the point where it's very, very difficult to measure, and it's to the point of almost being zero. Uh, Neutrinos typically pass through matter unimpeded with no detrimental effects. We have neutrinos passing through us all the time, through the planet, through us, through our various objects. They don't get turned. They aren't deflected. They just keep on going. The types of events or occurrences that are typically going to be associated with neutrino astronomy are going to be stellar nuclear reactions, supernova. These are probably the ones that have been most, at least observed up to this point. The spin down of a neutron star and cosmic rays or accelerated particles striking other atoms is something that really hasn't been used all that much. Like I say, neutrinos are very difficult to detect. Therefore, you're probably going to see some of the most, for lack of a better term, unique or bizarre type observatories. There are 2 examples here with respect to, I'll call them observatories. Really, they're detectors. The one you see on the left is the observatory that's over in Japan. It's well below the surface of the planet. What you see there, and if you can make it out a little bit, in the background, there's 2 guys basically in a rubber raft, and they're floating on this area of water. And there are various detectors above the water and below the water that are used to detect these neutrinos. There are very few that they're able to detect. So in some cases, they have to use statistical simulations, game theory, to try to, extrapolation isn't the correct term, but basically build it out a little bit so that they can study whether or not they're looking at an actual event. They're actually detecting a neutrino. Like I say, they're going through all the time, but being able to detect one is another story. But actually detecting a neutrino. A different type of observatory looking at the same thing is the Ice Cube Observatory, which is down in Antarctica. Here you can see at the very top, which is the surface of the ice sheet. You have these not photoelectric, but they are related to light. But basically, the detectors here are these various rods below the surface. They're built off of the bedrock. Here again, it's below a lot of ice. The whole point being that both in the case of this deep well water detector and the ice cube detector, being below the surface, that it's not necessarily the surface of the Earth, but being below the surface to an extent will improve the probabilities or the possibilities of being able to detect a neutrino and correlate it with some sort of astronomical event or object. If that wasn't bad enough, cosmic ray astronomy is a little bit more bizarre, I think. Here again, this is used to identify the sources of extremely high energies. We're talking, this is tetra and giga electron volts, very energetic events, more or less events, but protons, electrons, positrons, muons, and atomic nuclei. They're flying through interstellar space all the time. Some of it is generated by our sun. A lot of it is generated by these higher energy events going on out throughout our universe. You take a look at the bottom, taking a look at energy levels, directions, and compositions, supernova explosions, black hole accretion, and galactic magnetic fields. And that particularly, that's where cosmic ray astronomy comes into place. Somewhat affected by atmosphere, but ground-based high altitude balloons and satellite detections are probably the better methods. The one that I'm most familiar with, this is down at the Fred Whipple Observatory down in near Green Valley, up at Mount Hopkins. One of the observatories, because there's a number of different ones or different telescopes. They basically look like radio astronomy dishes, 3 dishes. I think they're about 12 meters in size. They used to have 4 of them, but they were used to detect cosmic rays, specifically muons. And there was a project that involved some citizen science going on where we were looking at different representations and taking a look at the pictures that were generated. I'll call them pictures, but graphs generated by this type of observations. It was a matter of being able to pick out when they detected a muon, and here again detecting a specific particle and trying to isolate those as opposed to all the other detections. It was certainly something that could be done automatically, but a lot of these citizen science projects in this specific case are used to help validate the machine learning and having some of these systems automated or being accomplished by AI. But this is one that deals specifically, it's called Project Veritas. I don't know if anybody else is familiar with it, but it is one of the installations up on Mount Hopkins. So cosmic ray astronomy. And that leads us to, there are the resources that I used. And thank you for your attention. Are there any questions?
Um, yeah,
No, Tom.
I've got a question or two
Okay.
about the gravitational waves.
If you're done with your bowl, I'll freak it.
One of the um, things I sort of have a little problem with, and maybe I have an idea how this works, I don't know, is that my understanding is that gravitational waves don't go in a medium as such. The medium is space-time itself. So space-time is expanding and contracting to give us a wave. So I guess my first question is that your understanding?
Yeah, it is. In other words, basically, one of the comments I made, not, well, certainly, it's subject to correction, but gravitating masses, have an effect on each other. And
Mhm.
certainly, even in our solar system, gravitational waves are probably emitted, but it's so low that they're not detectable, at least by current means. Whereas you take a look at, say, a neutron star merger, or a supernova, or the destruction, or a black hole merger, they are going to detect, they're going to emit gravitational waves. You're right, the medium, it's the vacuum of interstellar space. It doesn't require any medium. These are gravitational waves. To me, it's a little more difficult because when I talked about the medium, it mentioned the transport energy as gravitational wave or radiation. Okay, I'm not quite sure what gravitational radiation is. I mean, I
Yeah.
understand it very basically, but yeah, it's probably, in the simplest term, to me, it would be a ripple going through space time.
That's it.
And
Yeah.
Doug, correct me if I'm wrong. That's the way I understand it. And so, yeah, I
Yeah,
mean,
that's kind of how I understand that. But the paradox I have a little trouble with is since space-time is expanding and contracting, so would the wavelength of light as it's traveling through the expanding and contracting space-time.
So
okay,
So how do
you
we
said
detect
wavelength of
anything?
light.
Okay, so
so
so go
gravitational
to your
waves
picture of the detector.
gravitational waves themselves are not light. What's
Uh,
being measured here is they have a set of lasers that are staring and firing down at each other. When a gravitational wave, it essentially is a wobble in space, which minutely changes the position of the Earth and the position of the detectors. So this gravitational wave passes through the detectors and causes them to wobble in such a small, imperceptible way that's smaller than the width of a proton.
Right.
And that wobble is what is ultimately detected.
So Thomas,
Yeah.
if you look at this picture of the detector that he's got on the bottom of the slide,
Hmm.
so a gravitational wave will hit this detector, and essentially what happens before the gravitational wave hits, the two laser beams that are split going down the length of the legs, okay, the two different legs, are in phase with each other when they come back to the beam splitter. And so that's the picture on the top, but he's got number one. The two laser beams recombine at the splitter and they're perfectly in phase. So it looks just like a single laser beam there with the wavelength, just one wave,
Hmm.
okay, because they're in phase. When the gravitational wave hits the detector, it slightly alters the position of one of the masses or mirrors in one of the legs, but not the other leg. So now the lasers have a different distance to cover, and they're out of phase when they come back to the beam splitter in the middle, and that's the bottom picture now. You see the two
Yeah.
beams are out of phase. That's your signal that there's a detection.
Yeah, I get that. It's just it seems if the distance between the mirrors
That's why the
are,
legs are so long, is you're
are
trying to measure something that's really small.
yeah. Oh, and on that subject, I think I read that they actually bounce the light like thousands of times or something to get an effective longer distance.
That may
Oh,
be, I don't know.
okay, yeah.
Well,
Um,
remember, Tom, part of that effect of longer distance is having these two observatories separated by 1,100 kilometers. So that adds
oh, sure, yeah,
greater capability as opposed to just having one. And then it also helps verify that the signal they receive, because it should be received simultaneously, is a gravitational wave as opposed to something else.
yeah.
Because these are
Having
very sensitive. These are very sensitive detectors, and like I say, nearby seismic or sonic events can set them off.
having the two detectors a long distance apart allows you to um, uh, get an idea because the events may not happen simultaneously. There could be a time difference between
Uh-huh.
when the wave hits the two detectors because they're located 1,000 miles apart. There could be a slight time difference. It gives you a way to actually figure out what direction the wave came
Oh,
from.
yeah, true.
So it gives you an idea of where it is in the sky.
Hmm. Um, yeah, that makes sense. Um, an,
The other
another.
thing too, Thomas, I think you have to consider these aren't covered. Like most of the other methods, it's not covered under regular Newtonian physics. This
Oh,
is
I
special
know.
theory of relativity. I don't want to say it's bizarre, but I mean, here again, not totally understanding Einstein's theory, but this is completely a different area.
Right. Well, so what, and in that vein, when the space-time moves, the wavelength adjusts to, expands and contracts along with space-time. But what I'm wondering is if it's something to do with, and this is the relativity part that I don't get yet, but the maybe it's the speed of light So now we've got the wavelength changing, but maybe the speed of light isn't, and so therefore maybe it's a timing thing.
Not
Light
understanding
light
the
has
question.
nothing to do with this at all, and how
Okay.
you measure gravitational waves.
I mean, they are theoretically they move at the speed of light still, but it's not. Yeah, you're right. It's not related to light, and there are
No,
certain
I
wave.
don't mean the waves. I mean the laser light.
Oh,
You know,
okay.
how do you detect that they're out of phase in picture number 2 down there? How do you detect that they're out of phase
It's
if
similar. Think of it how noise canceling headphones work. It's kind of the same. It's similar principle.
I mean, I look at it this way,
yeah,
Thomas. It isn't this way, but imagine when you look at the top, you look at the diagram at the top. Can you
yeah.
see my cursor?
Yes, I do.
Okay, you look at this diagram at the top, you get this wave.
Yeah.
Imagine that you're looking at it on an oscilloscope. I don't think that's not the it's not the display you're looking at. But imagine if you're looking at this on an oscilloscope and you have this nice single wave going.
Hmm.
And then you have a gravitational wave come through. This is what you'll see displayed. It's
Yeah.
not that way, but uh, that's
There's
about
lots
the
of
easiest
technology for
correlation I can.
determining when two laser beams are out of phase.
Yeah.
That's an easy thing to do.
Yeah. Well, I'm just trying to figure out how do they get out of phase if space-time is expanding and contracting and the wavelength is following space-time contracting and expanding.
No, the wavelength of light is not following that. The wavelength of light, these are
Yeah.
vacuum,
Yeah.
these long legs are in vacuum. The wavelength of light is not being affected by the gravitational wave per se.
No, not by the gravitational wave, but
Okay. The
by
gravitational wave is changing the length of the leg.
yeah.
Right.
So the
Right.
light has to travel a little farther or a little shorter, and it gets bounced back. And the gravitational wave is it's a wave. It's not affecting both legs equally. It's affecting one leg and not the other
No,
leg.
I get that part.
So
Yeah.
there's a difference in distance that the laser beams have to travel, and that's what you're going to detect when you recombine them and they're out of phase.
Hmm.
You can compute what that difference in distance is.
Yeah. Okay. Well, I will continue trying to understand relativity. I do have another question that isn't related to the wavelength or the wavelength of the laser light. Um, Typically, what kind of frequency do we see of the waves, the gravitational waves? I mean, I hear about neutron stars or black holes rotating around each other, but how fast are they going, and what kind of frequency would that wave be? Are we talking 10 hertz, 100 hertz,
I just
1,000
put that
hertz?
back up. I just put that back up, the wave spectrum. And this is
Uh,
for the gravitational waves. And so you see the different events displayed way up top. You see the wave period. Understand some of these wave periods are not a matter of seconds or hours. These get into days, months, and years.
wow. Okay.
Okay. And so here again, trying to wrap your head around that,
Yeah.
because generally we think when you're talking frequency, we're thinking, okay, these are wavelengths, a meter to nanometers that we're familiar with more so. Well, a, this is just an enormous factor difference here. You look, and these are log frequencies. I
Yeah.
don't think they're
Okay.
necessarily megahertz, especially when you get into these wave periods. Like you say, the age of the universe. So you're talking 14, 15 billion years ago, and so it
Gotcha.
does get to be kind of difficult. And that's when you're looking at the cosmic microwave background uh, displays
Yeah. Okay.
detections.
Cool.
But I mean,
Wow.
there are, you take a look at the variation of these different events, and this is what you have with respect to the gravitational waves.
Hmm. No wonder my head hurts.
Hey, I got to tell you, I didn't want to get in the weeds too much on this. I mean,
No, that's okay.
from on the standpoint, it wasn't a matter of, you know, trying to consider the audience, and I used myself as a measurement. Certainly, there are certain aspects I understand a little bit better. And, of course, here again, this type of science is, like I say, it's been around for, maybe 2 or 3 decades, especially with respect to some of these more exotic forms. And, you're starting to see more and more. They're improving, technology's improving. You're seeing more and more papers on some of these different aspects with, especially with respect to gravitational wave. Uh, that's been kind of unique. I'm kind of surprised the fact, National Science Foundation had the budget for the 2 observatories in the United States, and I'm rather kind of surprised that they ever got built, given what's been going on, and not just recently. I'm talking over the past 2 or 3 decades, trying to get science funded. Some of the other things that have been funded, and not just in this country, other countries too. So it is somewhat impressive. There are a lot of different detectors and observatories out there, and they're not, like I say, not optical. Anything else? Otherwise, I will stop the share and turn it back over to Connor. Thank you. Thank you all.
Thank you.
Oh, thanks for the good discussion. Thanks, Pete, for presenting as always. And I will look forward to seeing you guys next month. Also, I am likely to be canceling the August meeting because I will be traveling for that. And Pete, I think that's fire season for you. So there won't be anyone to host the meeting. So but I'm still not yet 100% confirmed on that vacation.
Yeah. Let's hold that one. Yeah, Connor, because I may not be flying fires this year. So we'll keep that in mind. We'll talk about that in July.
Yep, just wanted to give a heads up to that one. So,
do you have presentations for next month?
No.
Okay.
I'll talk to you on email.
Yeah, send me the list. I'll take a look at doing a constellation next month if no one else wants to.
Sounds good. Have a good night, all.
Thank you.